Good afternoon and welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Kohar and this is the 21st of September. And this is Lecture 6, Rules of Inference. Good day. Hopefully everything is working okay. And hopefully everyone can hear me okay. Good day. Hello. I'm just making sure. Hopefully the the connection is stable enough. Can everyone hear me okay? Good day, good day. Perfect. Okay. Some people are lagging. Let's try. All right, let me see. Okay. I'm getting nothing. Okay. So I've just done a little bit of an adjustment. Is that working better now? I can't hear or see anything. How about now? I'm getting nothing now too. Okay. Okay, so you can hear me. Hopefully now it should be a little better. Okay, it's a lot better now. Okay. Perfect. Yes, it's just in OBS we have to adjust the video, the amount of the bit rate for the video connection. So I was just adjusting it and it seems to have corrected itself now. So that's good. So this is lecture 6. This is rules of inference. At the very heart of mathematics, we have the fundamental concept, and that's the proof. A proof is a convincing demonstration of the truth of a proposition, and it comes in two kinds. We have a formal proof and a mathematical proof. So again, just kind of at the heart of math, we have what is called the proof. We have two kinds. We have a mathematical and we have a formal. What proofs are demonstrations. So there's two kinds. So I'll make sure here's one, here's two. And proofs are demonstrations of something that we know is true. And in this course, we're going to be seeing two kinds of proofs. We'll be seeing mathematical proof, and we'll be seeing a formal proof. So what we're going to be actually looking at is the formal proof. And usually what this has is we start off with kind of like the foundation. Okay? And those foundations or kind of truths are called axioms. And from there we kind of build from that our structure. So a formal proof is then kind of a sequence of these things, these axioms. So we have these axioms, which are kind of like bricks. And we take these bricks, we kind of line them up, and it leads us to the truth that we're trying to prove. And this idea of a formal proof is largely a 20th century invention, and it was made by a man named David Hilbert, who is kind of one of the main leaders of mathematics. He kind of shaped mathematics in the early 20th century. And what he wanted to do, he wanted to place mathematics on a solid foundation by having a method that we could avoid with erroneous errors. So, that's what we're going to do today, is we're going to be looking at kind of these axioms or rules in which we can combine things together and generate something that is true. That's where we get into the rules of inference. That's the other thing to remember, is that the axioms are important. They have to be true. And these rules are what combine these bricks together. So if the bricks aren't good, it doesn't really matter how you glue them together, they'll just kind of crumble and fall apart. And that's what inference is all about. If you have good data, you're going to get good conclusions. This is what the inference part is. It doesn't make up anything new. It just kind of is examining the data. And similarly, if you have bad data, using inference, you're going to get bad conclusions. Okay. So what we'll do is we'll start to work through what are called the fundamental logical equivalencies. Fundamental logical equivalencies. And these can all be justified by using a truth table. Okay, so what I will do is we're going to say we're going to let P, Q, and R be any three propositions. Now these can be prime or compound. We'll say that this blackboard T is a tautology. And we'll use the blackboard F to be a contradiction. Okay. So the first one that we're going to start off with, now let's start to use some color. It's called Idempotence. And idempotence kind of meaning kind of like identity or the same thing. So the idea is that if I have, say, this one, which is P and P. Remember, this is the and. This would be logically equivalent to just P. So again, just P and P, that's the same as just P. So if I have, let's say I have a pink pen and I have a pink pen, well, there's still a pink pen. So what would the truth table look like this? Let's do the truth table would be P, and then maybe, let's repeat it again, P and P. I know, for such a silly, obvious statement, the truth table will look just like this. So true and true, so this would be true. And false, this would be false. And we see that this one and this one are equivalent. So therefore, P and P are logically equivalent to P. So I'll just put this up here. This is and. So it'll be like P and P is logically equivalent to P. So there's our first rule. And it's fairly straightforward for that one. Okay, so we did this with the and. Then the same rule we can come up with for or. So you can have P or P, and that's the same thing as just P, right? So again, you have a pink pen or a pink pen, it's still a pink pen. So again, kind of the basic truth table. Just kind of filling this out. And same idea. Remember that the or has to have at least one of them to be true for that to be true. So true and true, so that's true. False or false, so this is false. And again, that these are the same. So therefore, P or P is logically equivalent to P. And I'll write this out. So it's P or P is logically equivalent right. Are there any questions about that one so far for idempotence? Okay. So I'll take it as there's no questions. The next property that we have, this is associativity. So associativity, we've seen something like this in math previously. This is the idea where let's say I have be careful about this. So I have something like 4 plus 5, and there's the bracket plus 6, which is equivalent or equal to me writing 4 plus 5 plus 6. So just because I have the pluses here, it doesn't matter because I have the same operation. It doesn't matter where I put the parentheses around. It's the same thing. So, in general, if I had A plus B plus C, if I shift the brackets, this is equivalent. So this is in the case of addition, right? Similarly, we can do the same thing with multiplication. Maybe I should add these up. So I have 4 plus 5, that's 9. 9 plus 6 is 15, so there's 15 on this left-hand side. Over here, I have 5 plus 6, that's 11. 11 plus 4 gives me 15, so again, it's 15 on the right-hand side, 15 on the left-hand side. So again, by shifting the brackets, it doesn't matter. This is, again, if it's the same operation. If I have 4 times 5 times 6, that's equal to 4 times 5 times 6. Okay, so 4 times 5, that's 20. 20 times 6, that's 120, so that's 120 on the left-hand side. I have 5 times 6 here, that's 30 times 4, so that's still 120. So I have 120 and 120 on both sides. So it doesn't matter as long as the operation is the same. If I move the brackets, I get the same thing. So writing it like this, I can write it as A times B times C is equal to A times B times C. And this is for multiplication. Okay, so you're asking me, why am I going over something so basic with numbers that we have seen in high school? Well, the same idea holds for propositional logical equivalencies. So, with like the addition, let's work with the ands first. So with this, I could say P and Q and R. I'll just write this again. P and Q and R. And what I'll do is I can put the brackets around here. So this is my left-hand side. And I could take these brackets and move them over so that they're around Q and R. So over here, that's what I'll do right here. And these are logically equivalent. So that would be P and Q and R is logically equivalent to P and Q and R. The truth table looks kind of like this. P, Q, and R. We'll do P and Q, and then we'll do the P and Q and R. And over here, I'll do the Q and R. And lastly, P and Q and R. So I'll make sure I number this. This is number 3. And these are just the numbers that are in the book. So I have three propositions. So that means that I'm going to have 8 rows. Just alternating from the last row here, or last column. And now, again, we can start to construct our truth table. We have the and. So I'm looking at this column, the P, and then I'm looking at the Q column. And for the and to be true, both of them have to be true. So this is true, true, false, false. Looking again, F and T, so this is false. F and T, this is false. Okay. And then I'm going to take this column and this column, the P and Q and the R, and I'll do the and. So I have true and true, so this is true. True and false, so this is false. I have false and true, so this is false. I have false and false, so this is false. False and false, this is false. False and true, that's false. And false, that's false. Okay. The next thing, I have Q and R, so I need to use this column right here and this column, the Q and the R, and using the and. So this is true, this is false. This one is false. This is false. This is the true. This is false, false, and false. And lastly, I'll take this column and the Q, and I will put that together. I'll probably just see if I can cover this up. Cover this up here. Also cover this up here. There we go. So P and Q and R. So true and true. So this is true. Here it's false. 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 Okay. So with that, now to look at the logical equivalence, make sure that we're looking at the right column, or I mean the correct column, not. So we are looking at this column here. This column here. Same thing over here. Okay, so now we just go through and check to make sure that each of these lines are the same, and they are. So, again, they're the same. So therefore, P and Q and R is logically equivalent to P and Q and R. So while we have it for the and, this also works for the or as well. Okay, and that is what we call the associativity. Oh, somebody has said if P and Q are both false, aren't they true? No. Let me just quickly go back, and somebody is just asking about the and. Just remember, okay, so here's our and. So P, Q, and we'll have the P and Q. True, true, false, false, true, false, true, false. For the and, it has to, both of them to be true. So both P and Q must be true for P and Q to be true. Otherwise, it's false. So, again, we can construct this again. Here's the true. Both of these are true, so this is true. One of these is false, so this is false. Again, here is false, and this one is false. So this would be the truth table for the and. Does that answer the question? Okay, perfect. It's good to tell me if I answer the question, then I can move on. Unfortunately, I can't see people. This isn't like real life. So I have to rely on you confirming that I got it. I answered it satisfactory. Okay, so the next one that we will have is commutativity. So here's commutativity. And commutativity is where the order doesn't matter. So for instance, if I had 3 plus 4 and 3 plus 4 is 7, I could have also said as 4 plus 3, which is still 7. So just writing this out as A plus B is equal to B plus A. The order doesn't matter. So I can change them and they're still equivalent. For multiplication, same thing. If I did 3 times 4, which is 12, it's the same thing as writing 4 times 3. And that's still 12. So Commutativity is just about changing the order and it's still being the same. If I go back to using the pink pens again, right? I have a pink pen and I have a pink pen. Oh, let's say I have an orange pen. So I have a pink pen and I have an orange pen. Well, this is equivalent to me saying I have an orange pen and a pink pen. These are, let's see if I can write a little. These are logically equivalent, right? So I can have if I just kind of put in some words here. So I could, for instance, I could say again, I have the pink pen and an orange pen, which is logically equivalent to me saying that this is an orange pen and a pink pen. So this works for the and. Also, this works for the or. So I could have a pink pen or an orange pen, which is also equivalent to me saying an orange pen or a pink pen. The order doesn't matter to us. So let's put these to the side. So that means, let's say, here's 2.5. So I said instead of pens, let's use propositions. So we could say we have P and Q. And that's logically equivalent to me exchanging the order. So I could say Q and P. And you can quickly check this using a truth table. So we can have P and Q, and then we can have Q and P. So over here, I'm going true and true, so this is true. I have true and false, that's false. False and true, so this is false. And false and false, that's false. Now working on the Q, I'm going from this column to this column. So I'm going from Q, so here's the true and true, so this is true. I have the false and true, this is, whoops, I almost wrote it down as true, but this is actually false. So false and true, so that's false. Then I have true and false, so this is false. And I have false and false, so this is false. So again, these two columns are the same. So since that they're the same, that means that they're logically equivalent. And we can also write this. So this works for the and. This also works for the or. So I have P or Q. This is logically equivalent to Q or P. And the tables, you do the same thing again. You construct a table and you can show that in fact P or Q is equivalent to Q or P. So is everyone okay with that so far? Okay. And we have one more. Let's write number 4 here. There's also another one that we have. Yes, perfect. There's another one that we have because we had the biconditional. So we had P if and only if Q is logically equivalent to, I can just change the order, Q if and only if P. So that's what I want you to do, just to take 5 or 6 minutes, or well, maybe 2 or 3 minutes. And we'll just do this. We'll have P and Q as P if and only if Q. And over here you can do Q if and only if P. And just remember that this is P if and only if Q, which means that is true if P and Q have the same truth value. Okay? So take 2 to 3 minutes and just complete that. And don't worry, I'll do it too. I'll just... won't let you have all the fun. I'll do it as well, so... Okay, so I think this is what I got. Did everyone else get the same thing? Perfect. That's good to see. All right. So what's the next kind of okay. So we have distributivity. And this is, let's see, the example that we'll use from arithmetic. Again, I'll use addition. So okay. So in distributivity, the idea is that I am going to distribute this 3 times to the 4 and to the 5. So it gets applied to here, and it gets applied to here. So it goes 3 times 4. Plus I have 3 times 5. And if you don't believe me, so we have 4 plus 5. So 4 plus 5 is 9. And in front of here I have the 3. And that is equal to 27. And over on the right-hand side, I have 3 times 4, that's 12, plus 3 times 5, which is 15. So 2 plus 5, that's 7. And 1 is 2, so I have 27. So they're the same on both sides. You might ask now, okay, what if this was flipped? What if I had the multiplication here and I had the plus over here? So same thing, we can write 3 plus, and I have 4 times 5. What does that equal? Okay, so again, doing the distribution, I have 3 plus 4, and then I'll have the times. Put that right here. I'll also be applying it to the 5. So I have the 3 plus 4. There's the times. Then I'll have 3 plus 5. So over here, just checking, I have 4 times 5, that's 20, plus the 3 gives me 23. Over on this side, I have 3 plus 4, which is 7, times 3 plus 5, that's Did I miss did I do something incorrectly? there anyone that's watching? Maybe try 3 plus 5 times 4. We aren't any good at math. Addition isn't distributive. Good. So that's really important, okay? And I wish a lot of people make this mistake. So, what we'll do is just put it. It doesn't quite work like that. You're right. So you got to be very careful about that. It doesn't quite work the same way. So, but what I can show you is I can change this order here. So same idea. But what I will do is I can show you that this is still true. Okay. And same idea applies. So over here I can have 4 times 3, and then this plus comes here, and then I have the 5 times 3. So we got to make sure we check, right? So I have 20 times 3, that gives me 60, and over here I'll have 12 plus 15. Oh, and we still keep mixing this up, because that's 7, and here is 2. So just be very careful about this. Okay? But what I can show you is we'll use some propositions, and I can come up with something that's very similar for the distributive rule. Break time. Well, what I will do is for people that need a break, that need to go run to the washroom or something. Did somebody catch my error? I hope so. Perfect. So 4 plus 5, that's 9, which is 27. Is that correct? Okay, so somebody has corrected this. Does this make more sense now? Is this correct? Everyone else? What does everyone else think? Yes? Okay. So what I'll do is I'll rewrite this in good. Thank you. That's very good. Please, again, keep an eye out for that. Okay. So somebody wanted a break. What we'll do is I will give you the rule for, here we go. Call this is be 2.8. Sorry, don't worry. And same thing, we can just apply this. So that's the rule. So you can see I have the P and Q or P and R. And so for those that are going to go on break, for those that are going to be staying here and working, what I want you to do is we'll fill in this truth table. So we'll do the Q or R, then we'll have the P and Q or R. And similarly over here I'll have the P and Q, I'll have the P and R, and then we'll combine these two together to get P and Q or P and R. Okay? So if you just need to go run to the washroom, take about maybe 3 or 4 minutes. Well, maybe we'll do 5 minutes. So we'll pick that up at 3:45. Okay, so we've had our 5-minute break. And there we go. It's 3:45. And this is the truth table that I got. So really, we're looking at this column and this column. For this column, I had 3 truths and then 5 falses. And over here, I had 3 truths and 5 falses. Looking at this column and this column, which is this column corresponds to the left side of the equivalence. On the right-hand side, this is the right here. And we found that they are the same truth table, so therefore they're logically equivalent. Did everyone get the same truth table? Perfect. Good. Excellent. So the same thing, I can, up here I have the and in this case, I'm just going to switch this. This is going to become goes from and to or, and I'm going to go from or to and. So what that happens is I distribute this. I have the P or Q. So that becomes P or Q and P or R. Now, because we've saw something like this where we didn't quite work out, you might be worried that what I've written here is incorrect. You would have good reason. But what we can do to reassure ourselves is we can do a truth table again. So again, P, Q, and R will have the Q and R, and then we'll have the P or Q and R. Then we'll do, so this will give us the left-hand side here, and on the right-hand side I'll have the P or Q. On this side I'll have the P or R, and then lastly I will take this column and this column and combine them together with the and. That will give us our last. So that I'll be able to prove to you this. So again, I have 3 propositions. So that means that I'm going to have 8. So 2 to the 3. So 2 times 2 times 2. So then on this one, we'll take this, maybe I'll cover that up. There we go. Cover this up. So that I'm working with this column and this column, so I'm going to be doing the and. And again, both of them have to be true for this to be true. So true and true, that's true. True and false, that's false. I have a false here, there's a false. There's a line where it's all true, so I'll put a true there. There's a false, there's a false, there's a false. So okay. Then cover up this. Oops, not long enough. There we go. We'll do the or. So at least one of them has to be true for this to be true. So true or true, that's true. So there's a true, true, true. So up to this point right here, that's true. I have a true here, so that makes this true. And then the rest of them are false. Okay. Now I'm using this column and this column. So this is P or Q. So again, here's true. There's true. That's true. True and false. That's true. That's true. That's true. And this is false and false. Now I'll have the P or R. Unfortunately, I need to trim that down a little bit more. There we go. Cover that up. So looking at this column and this column, I have P or R. So this is true, 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 true. Now I have false or true, so that's still true. False or false, that's false. False or true, that's true. And false or false, that's false. And lastly, I will take this column and this column, and I'll do the and. So true and true, that's true. True and true, that's true. And the last ones are false. Okay, and the moment of truth is, what were we trying to prove in the first place? Well, we were looking at this left-hand column right here. So this is where we'll look here. Right, that's the call. Got to make sure, right? P or Q and R, good. And this is the right-hand side, P or Q and P or R. So this is the column over here that we wanted. Okay, put that over here. And are those the same? Yes. Yes, they are. Because if I go down the column, so these are all true, and then I have 3 falses at the end, so they are the same. So therefore, P or Q and R is logically equivalent to P or Q and P or R. Number 6. This one is called De Morgan's Law. De Morgan's Law. Oh, and I should have done that in purple. So De Morgan's Law, you can think of it as distributing a negative. And what do I mean by that? Okay. Well, let's say, I'll start using some color in here. So let's say, for instance, I have P and Q. And we're going to have the negation out front here. Well, what the what De Morgan's Law says is that we'll take this, and we apply it to this, we apply it to this, and we apply it to that. And what happens is that we get the negative applied to the piece, so it becomes negative or maybe I should have written negation. So I have not P we'll have the negation applied to the or, so it switches from an or to an and then the negation is applied to the Q. So, again, we can do a truth table for this. We can have P, Q. Then we'll do on the left-hand side, working on the left-hand side first, we'll do the P or Q, and then we'll apply the negation to it. So not P or Q. And then that will be done, that will be done on the left-hand side, and then on the right-hand side, we'll have not P, not Q, and then we'll do the and, not P and not Q. And what's nice about this is we only have 2 propositions, so we're going to have only 4 lines. But again, this is nice, straightforward. Just remembering what our or is. It's true if at least one of them is true. And then this column we just flip, so it goes from true to false and false to true. We'll just flip the values for P, so it becomes false, false, true, true, whoops. And for Q, false, true, false, true. And looking at this column and this column, we'll do the and. So for this to be true, both of them have to be true. So this is false, this is false, and this is true. So again, looking at this column and this column, this column, this column. So this is the left-hand side here, and here's the right-hand side. And they are the same truth table. So what we have done is we have proven that not P or Q is logically equivalent to not P and not Q. Here's 211. So I can also have by just the case of where we have, so this was the or, what if we had the and? So I'll have P and Q. That's logically equivalent to. So what we do here is we apply the negative to each term, or each symbol here. So this becomes not P not and, well, we'll flip that. So that becomes from an and to an or. Then the not is applied to the Q, so it's not Q. Okay, so we'll do the same thing. We'll do proving the left-hand side here. So we'll have the P and Q. We'll have the not P and Q. Then we'll be done on the left-hand side here. On the right-hand side, we'll have not P, not Q. And then we'll finish it off by applying the or to these two columns. So we'll have not P or not Q. And again, just two propositions, which means that we'll have 4 lines. This is just our and, which then we flip with the negation, so it becomes from true, false, false, false to false, true, true, true. And we're going to flip the values from true to false, and same thing with the Q. And then doing the or, so false or false, that's false. False or true, that's true. True or false is true. And true or true is true. Then, again, we just look at the columns that we want. This is the left-hand side. This is the column that we want right here. So again, these two columns are the same. So therefore, not P and Q is logically equivalent to not P or not Q. So what we should do these are kind of our fundamental. Just to review what we've done so far. What we had done was the idempotence. Of course, I mixed that up. Idempotence, and that was that P and P is equivalent to just P. I could have P or P, which is equivalent to itself. We did the associativity. So again, I had with the and, if I have the brackets here, I have the same operation, and I can just shove those brackets. So I have the P and Q and R. And same thing applies for the or. As long as they are the same operation, I can move those brackets easily. We had the commutativity. So that the and, I could have P and Q is equivalent to just Q and P. And same thing with the or, I could have P or Q, and that's equivalent to Q or P. I'm just changing the order. So we had idempotence, associativity, commutativity. We had the distributive property. Where we have, oh, and we can't forget, we also had the biconditional. So if I had P if and only if Q, I can exchange that order as well so that I have Q if and only if P. Okay. We had the distributive property so that I had P. So I have P and, so inside here this would switch. So again, with the distributive property, if I have different connectives, I have the and there's the or, you know, I can't just move these brackets like I could with the associativity. They have to be the same symbol. So in this case, I have to apply the distributive rule. In this case, I'm applying the P and Q, or P and R. And similarly, if I did with P or, so just changing that, I could have P or Q. Oh, be careful that that should be the and. That I have P or Q and P or R. There's our distributive rule. We had our De Morgan, which is kind of like our distribution or distributive rule for the negation. So that if I had not P, I think we used the or first. So not P or Q, I'm just applying that negative or the negation to each of those. So it's not P, the negation of the or becomes the and and applying the negation to the Q. There we go. And same thing applying it to the AND. Then I have not P or, so it's flipping the AND to an OR, and Q. Okay, so those are what we've covered so far. Just as a review. Here's 7. This one is called identity. So I have P and a tautology. What do you think that's logically equivalent to? P and a tautology. What do you think that's equivalent to? Well, what we'll do, since we don't know, we could maybe have a look. Let's just write this out. I have P, I have a tautology, and then we'll do P and a tautology. So, just P, tautology. These are all good guesses. Yeah, let's see what happens. Let's write out, let's say I don't remember. So, let's say I forgot my, that lizard isn't supposed to be there. So I have true and false for P. Those are the possible ways I can assign to P. With a tautology, it's always going to be true, which means then that if I look at here, I have P and a tautology. So it's P and, true and true. That gives me true. And false and true, that's false. And if I look at this column here, oh, I could just use a highlighter. Exactly. So just looking at that, these are the same. So therefore, P and a tautology. So this one here is equivalent to just P. So that is our rule right there. Somebody asked about P or F. So we can try that. P or a contradiction is logically equivalent to. So again, I can show you, we can write this down. P or a contradiction we won't write all truths. These ones will be all falses. So looking at P or F, this is true or false. So this is true. False or false, that's false. And then looking here, these are the same. So therefore, P or a contradiction is equivalent to just itself, P. This one is called Domination. And the reason for this one you can think of it as it just kind of overpowers, or it just obliterates it. But it's P or a tautology. And because we have the or here, for P or something to be true, at least one of them has to be true. But this tautology is always true, so that means that this will always be true. And if you don't believe me, we can always do the truth table for it. So again, just kind of writing it out, I have P, a tautology, and then I have P or a tautology. So again, I just have two lines. So again, I have true or true, so that's true. And in this case, I have, oh, oops. Did somebody catch something that I did wrong? That's supposed to be a tautology, right? So again, I have the false or true, which makes this true. So that's right. Tautology is always true. Which means then these are the same. And so we have shown that P or a tautology is always a tautology. Okay, so this is for our domination rule. We'll have P, and then there's a blank. Contradiction is equivalent to a contradiction. What symbol do you think should be in here? And yes, perfect. And we'll do this. So let's see. Again, for this to be true, both of the propositions have to be true. But because I have a contradiction, which means that this is always false, I will never, ever have where both of these are true. So what I mean here is, I'll write, right? There's my truth table. And I do my and. I have a true and a false, but it's always going to be false. So these have to both be true so that I can have a true, but it's not. So this is false. I have false and a false, so that's false. And so I have the same. So those are logically equivalent. Okay, so I'll put this over here. We did the identity. this out over here. So, idempotence, associativity, commutativity, distributivity, De Morgan, and then we've got the identity, so then I have P and a tautology is equivalent to just P, and then I have also that I have P or a contradiction would just be P, and then we have domination, so that I have P or a tautology, which means that I'm always going to have a truth value. So that will always generate true. And if I have P and a contradiction, this will always generate a contradiction. I think I'll show you one more rule. Here is, let's do, this one is called let's do excluded middle. So with the excluded middle, we had seen something we had seen this one before. So I have P or not P. What is this logically equivalent to? What is that equivalent to? Yes, it is a tautology. Good. Yeah, it's a tautology. And we had done this before. So all I would say is go back to, this was kind of our, this was our example. This was our example for a tautology. So there was the excluded middle. We also had done we have a contradiction too. Let's we had P and not P. So that is a contradiction. Again, that was our example for a contradiction. And if you want to see what the truth table was, you can just flip back into your notes. We had done that during that lecture. So that was our contradiction. And I will show you the implication rule. And these are enough rules that you can be sufficiently dangerous. So, what's the implication? One, we have P implies Q is equivalent to not P or Q. And again, if you don't believe me, just a quick truth table will show you that this is correct. So just doing our quick truth table for this, there's only 4 lines. Now, as remembering our implication, I stepped into poison ivy, I got a rash, this is possible. I stepped in poison ivy and I didn't get a rash. No, you are definitely going to have something. You didn't step in poison ivy, but you got a rash, this is possible. Not all rashes are caused by poison ivy. I didn't step in poison ivy and I didn't get a rash. This is possible as well. So, true, false, true, true. This is the implication table. And I'll take the P. We flip the values. And then using the not P and the Q, so it's going to be not P or Q. So it's going to be false or true. So this is true. False or false, this is false. True or true, that's true. True or false, that's true. And just quickly looking at this. Oh, I should have just, there we go. Same truth values. So therefore, P implies Q is logically equivalent to not P or Q. Okay, so let's just wrap that up. Just to make sure that we've done, I'll have a summary at the end of the lecture here. So we have, I only have a couple, about less than a minute. So we have the domination. We have the excluded middle. Which was our to be or not to be. To be P or not P, that is a tautology. We had the contradiction, which is P and not P. That's a contradiction. And lastly, we had our implication, which was P, or P implies Q is logically equivalent to P, not P or Q. Okay, so we covered the rules of inference. If there's any questions, feel free to send me an email. Tomorrow I'll have some office hours in the evening. We can do this over Zoom. I will post a link on the Moodle webpage. Again, working through the assignments. We have one of the assignments have been posted. Just a second. So just quickly switching over to my screen. Here we go. And we'll just scroll down, and we have posted assignment 2. So you can click on that. There is our assignment right here. So doing the exercises from the textbook. If there's any questions, again, feel free to drop by the office hours tomorrow night. I'll be doing it probably maybe from 7 to 8. I'll post again that on the Moodle webpage. These videos remain on YouTube after the stream ends, right? I'd like to review. Yes, of course. These are available after the stream is, they'll stay there. Yes. Perfect. Thank you for adding them to a playlist. Again, any questions, please feel free to send me an email at my RMC email address. And I will see you all tomorrow. Thank you everyone for tuning in, and thank you for participating in the chat. Have a good night, everyone.